Good evening once again. I think we can start now.
Yeah, good evening, sir.
Good evening, sir.
Yes, sir.
Okay, somebody let me mute everyone. Yes, today we want to quickly discuss ANOVA, understanding ANOVA. Yes, as you all know, when we compare two means, that is, when you have a quantitative variable, what I mean by that is something that you only give number like age, like blood pressure, anything that you can only give number. They are all quantitative variable. You summarize with mean, standard deviation. You can also summarize with median. But for categorical variables, something that you cannot give number is either like male, female, socioeconomic status, upper, lower, middle, ethnicity, or even the department or the profession. Think of anything that you cannot accrue number. If only you give number is just coding, those are categorical variables. But the quantitative variable, which you summarize as mean. If you want to compare, you have two groups, and you want to compare the quantitative variable, we all know that we use t-test. T-test used to compare two means. Although sometimes we have one sample t-test, you have more mean, but you are comparing it one sample, the mean in that one sample with another mean in the population. Whichever way still mean. Even when you are having pair t-test where it's only one group, but you carry out your observation on two occasions. Even though it's not the two mean you are comparing, but it's the difference between them. Whichever way, there are two mean ab initio, two measurements. So the t-test is about comparing two mean. There are situations where you have more than two groups, like 3 groups, like 4 groups, and so on, and you have quantitative outcome you want to compare. So you compare using ANOVA. And the reason for using ANOVA instead of using t-test, one of the things we want to look at this evening, and I will not be able to finish up with understanding ANOVA in one lecture. But let's just start. So comparison of means, you either compare two means or you compare more than two means. So when it's more than two means, either 3, 4 is the same method you use. It's quite different from the two means, which you use t-test for. Now, if you remember when we're discussing how do I call it, hypothesis testing, talking about assumptions around hypothesis testing. I remember saying that a t-test is the simplest to understand hypothesis testing. And all hypothesis tests, they are the same thing. They are just like the same, it's just the same thing that put on different cloths. All hypothesis tests, the same logic. And for you to be able to conceptualize the hypothesis test mean t-test is the simplest, that is comparing two mean. Now, look at what we have here. You see, give example of independent t-test here. We also have dependent t-test. This one is comparing two means now. If you look at the first one, you see observe difference between sample means minus expected difference over estimate of the standard error of the difference between the two samples. Actually, what you compare in hypothesis testing, what you do is to look at the difference between groups. You can call it the systematic variability of variation or variance. Systematic variance. When the word systematic means the way you design your study. You know, when you have urban rural, you have two groups, and you continue maybe hemoglobin concentration. You want to compare hemoglobin concentration, the mean hemoglobin concentration in the two. Because it's you that designed the study to be two groups like that. So that's why the word systematic has to do with the design. So when you imagine now, if we actually use the example of blood sugar between male and female, imagine you have two groups, male and female, and when you calculate the average blood sugar for female to be 65, average blood sugar for male to be 60, you can see the difference is 5. That difference you see is the observed difference. So the values 65, 60, they are observed values, and the difference between them, they are observed different. So it is very clear that the mean for this one is 60, the mean for this one is 65. So the difference now is the systematic variation. The variation due to the fact that you are trying to compare male and female. But there is what we call inherent variation. Inherent variation means that when you don't even try to divide people into male and female, there are variability in the blood sugar in the population. For example, you have female have their own blood sugar. Even the mean for the female is 65. There are some male that have more in the population that have blood sugar have higher than that mean for the female. There are some male that have higher blood sugar than some female. Then even the male, you say that the mean is 60. There are some female that have lower blood sugar than the 60 for the male. There are some female that have lower blood sugar than the male. So you see, in the population, there is this inherent variability. That one is, how do you measure that? The only way to measure that is through the standard error. So we'll not talk about the nitty-gritty of the standard error here, but when we're discussing introduction to inferential statistics, when we're talking about sampling distribution, I demonstrated standard error. So people will say, what is standard error? They say population standard deviation. No, it's not true. Standard error is the standard deviation of sampling distribution, but it is believed to be equal to the population standard deviation. So what standard error does is doing two things. When the standard error is very small, it may mean that the attribute naturally in population, they are close, they are not widespread. For example, now, if you compare height and weight in the population, the value of height are closer than the value of weight. The value of weight, the weight of people adult, you know, there are some people that are very light, big, they have high weight, while some have smaller weight. So the variation when it comes to weight in the population is much more than the height. So you can say that naturally the standard error for the height will be smaller than that of the weight in the population. So when the standard error is small, it may mean that the attribute they don't vary much in the population. That is the inherent variability in the population. But when the standard error is very large, it means that the attribute, they are far apart. People have different value. The value from one person to the other very much. That's why the standard error is large. Another thing that standard error will point, if it is very small, the estimate, you know that when you are dealing with your research work, you take sample. Whatever you summarize is for the sample. The is called statistics. The real summary you are interested in as a researcher is the parameter in the population. And the parameter in the population is you cannot know it unless you study the whole population. It's unknown, it's only God that will know it, unless you study the whole population. But whatever you get from your sample is an estimate. That statistic you have from your sample is an estimate of the population parameter. So when the standard error is small, it means that our estimate is not too far from the real population parameter. Then when the standard error is very large, whatever estimate you have, it shows that it may be too far, it may be far from the real value in the population. Can you see the two ways you can use standard error now to really know how close or how far the estimate you get from your sample is from the population parameter? Another thing is how you know maybe this attribute, are they very close in the population or they are wide apart, they very much in the population. So you see the reason, this last one I just said now is the reason, is what they are using here in hypothesis testing. You look at the variability, the standard error is what measures the inherent variability in the population. So now, when you are now saying the blood sugar of male and female differ by 5, so the intelligent people want to know, this 5, is it by chance? Because sometimes If we do it again, we may even see that the male is more than the female. So how do we know that this observed difference is actually a true difference? It's not a difference that is due to chance. So intelligent people ask, okay, why can't we put this observed difference over the inherent variability? That what it means that if the observed difference, which is the systematic variability, is large, and the is some way either large or not, there's somehow it's a particular value, and the inherent variability is as big as that one also. Will you say there's a difference? If the observed difference is not too far from the inherent variability, that's almost the same. That shows that observed difference is not a true difference. It can just be to chance, because even naturally within the population, it can vary like that, like what we are seeing between male and female. So that is why the logic behind hypothesis testing, all hypothesis testing, is to put the systematic variability over the inherent variability. So the systematic variability will serve as numerator, while the inherent variability will serve as denominator. You know that if two things are the same, 35 over 35 will give you 1. Any two things that if you divide, it will give you 1. So if the inherent variability and the systematic variability are the same, when you do the statistic, it will give you 1. But if the even inherent variability is even much more than the observed variability you observe it, when you divide it, because the inherent variability is the denominator, it will give you 0 point something. It will not be up to 1. That should just forget about it. But if the systematic variability, before you can say, this difference is a big difference. So the difference I've observed, which we are using as numerator, if it's far bigger than inherent variability, it will be greater than 1. Because if the numerator is far bigger than denominator, it will be greater than 1. Not only that, if there's real difference, that variability, the systematic variability we are seeing is a real difference. It will be far greater than the inherent variability. It will be far greater than 1. It will not reach a critical level, and that's, it has reached critical point that no, this one is not due to chance occurrence. It's a real difference. So that is where the logic behind the critical value for each of the statistics, either you are talking of chi-square, you are talking of F test, or you are F statistics, or you are talking of T statistic, whichever statistic you are talking about. That's the logic behind that critical value. It is when the inherent the systematic variability is far greater than the inherent variability. Oh my God, this one is not due to chance occurrence. It's a real difference. So that is what just portrayed here. So I don't want us to waste time on that, just to wet the ground. You will see that for t-test now, which is the simplest for you to understand hypothesis test, we have two type display here. I think I thought that I just displayed 2 types here: the independent sample t-test and pair sample t-test. So although this lecture is not about t-test, the independent, I will just keep, but just understand what I've just said now. So in our lecture on t-test, we actually explain the difference between the two. The first one is the difference between 2 means. Second one is the mean of the difference. So there are 2 different things. But let's proceed. So we have established the fact that for 2 means, you use T to find the difference. But why I put that in here is for you to understand the logic of systematic variability and inherent. Some people say non-systematic variability. Inherent variability just means the one that is there within the population. But the systematic is the one that is due to their design, what we are trying to find out, the difference. Like someone that did urban rural, you want to see the difference between urban and rural. That's where the word systematic is. When you say something systematic error, you know what it means. It's based on the way you carry out your study, the study design, everything, the way you do your study. Systematic error has something to do with that. So when you say systematic, is the design. While the non-systematic is something that is inherent in the population. It's not based on what you do. Now let's look at the comparison of more than 2 means. Now, ANOVA, the meaning is analysis of variance. Now, ANOVA is a group of statistical method employed to compare the means of 3 or more groups. So it is good to understand that t-test is not used to compare means of more than 2 groups. Therefore, it is good to have an understanding of the reason. And the reason t-test is not used is because of the concept of family-wise error. So let's look at this family-wise. What does it mean? Sometimes, when you see formula factorial, let me just first of all, I will come back to that. I don't like starting with formula that will, first of all, trigger people's, make people to feel somehow. Now, there's something here that I want to, I think I have it somewhere. Yeah, okay, let me just, there's a table. Well, maybe it's not here. Now, what I just want to, okay, imagine you compare 2 means using t-test. Now, if you set your level of significance at 0.05, which is 5%, that is the level at which you want to reject non-hypothesis. The probability that this difference is due to chance. Once the probability is very big, you say, oh, it's not that. Oh, if it's 50%, 0.5, so it's like gambling now. So the probability that whatever difference is due to chance, that's why it's not a true difference. Because if it's due to chance, if you do it again, you may not even find different thing. You may find another thing, different way. So, but if the probability is becoming small and small and small, as low as 0.05, which is 5%, that is, or less than that, you just assume, okay, the probability that this finding, the difference I've seen is due to chance is very small. Let's say that it's not due to chance, so it's significant. The difference is significant. Another way of saying is that the probability of committing type 1 error, because type 1 error say that rejecting no hypothesis is true. Because no hypothesis there's no difference. But alternative hypothesis there's the difference. So if it tells the no hypothesis, and if the no hypothesis is true that there's no difference, then you now say you reject it, you say there's a difference. That probability of saying something is there when it is not there is still the p-value. Is the probability that whatever find is due to chance. So of course now, if the probability that something is not there and you say it's there is very high, that shows that you have committed type 1 error, that something that is not there, you say it's there. It's an error of commission. So now where I'm going is that 5% usually is an arbitrary value. The logic behind 5% is 1 out of 20. 1 over 20 is 5, 0.05, 5%. 1 out of 20. That is, if 1 out of 20, we can see that it's significant. It's not due to chance. But anything greater than that, you believe that the probability is too high. Now, the 1 out of 20, which is 0.05, is what we usually say, but you can be stringent. If you are so stringent, you can see 0.01, which is 1%. But nobody take anything greater than that 5% from anybody. Say 10%, no. Nobody take that. You can take, but conventionally people use 0.05, 0.01. But in between 0.05 and 0.01, there is 0.04, 0.03, 0.035. If you do it, there's nothing that has stopped anybody from using it. But it has become a convention that's 0.05. Now, if you have set that 0.05, if you now do, imagine you have 3 groups now, you want to compare the mean. You know, if you have 2 groups, you want to compare the mean, how many ways you can combine 2 groups? It's just to pair 2. It's only one way now. Group A, Group B, you pair them just one way. But if you have 3 groups, you want to compare 3 means, A, B, C. How many ways can you compare it, pair them? It's 3 ways. A and B, A and C, B and C. There are 3 ways. It means that if you have to do 3 tests for 3 groups, you have to bring Group A and Group B and compare the 2. Group A and Group C and compare the 2. Group B and Group C and compare the 2. So you do 3 t-tests. Now, if you do 1 t-test, your error family, you set your level of significance to be 0.05. So if you remove that 0.05, from 1 is to give 0.95. So if you now do test 3 times, you now multiply that 0.95. You multiply 0.95 3 times. 0.95 times 0.95 times 0.95. If you now remove it from 1, whatever I give you, it will be high. It will be around 40%. That be 0.145. What we are saying now is that whenever you do the test 3 times, your p-value you say as 0.05 is actually 0.145. That is, what we said as 5% is actually 14.5%. That's what it's saying. Just a minute. Let's yes. So look at what I have here. Forget about all those first, second column. Okay, let's look at the first column. What I was trying to explain. Let's look at the first column. The first column, let me use this spot slide. The first column talks about number of K group, number of group you are comparing. For 2 groups, this is the one you use t-test for. You look at the level of significance, you say is 5%, 0.05. P-value is 0.05, which is 5%. Now, this first row is for t-test because you are dealing with 2 groups. So what this formula in the second row is just to use combination. How many times, how many ways can you pair 2 things, 2 groups? So you can only pair, that's where a 2 factorial over 2 minus 2 factorial times 2 factorial making 1. So you can only pair 2 things once. Now that is only one, you can only do 1 t-test. Now how many, the number, this one, 3 groups, how many ways? You can only pair 3 times, the way I explained. So in that situation now, the number of pairs of possible is 3. And when you do the calculation as equal to what I said, it gives you, instead you have set your level of significance to be 0.05, but it's actually 0.143. You don't know that you have made a lot of error. The ordinary way of saying it is that there's no way you do many tests. At least even if one would be significant. That's just when you do many tests, even normally nothing should be significant. It's just like somebody that is gambling. It's just like somebody that is going for exam 7 times. Even for the fact that he passed 7 times doesn't mean the person has improved. It may not mean that the person has improved. It may mean that as he's doing it, he's getting on. So by chance, no gambling. It's just like in medical school, most of us that are doctors and even health profession, you know that there are some questions they set for you, yes or no, yes or no, yes or no, yes or no. And whenever true or false, these true or false in medical exam, sometimes you can sit down, they might set up to about 1,000 questions or 500 over 500 questions. You are in one sitting, true or false, true or false, true or false, true or false. But if they don't remove negative marking, even somebody that has not gone to school, you cannot give 1,000 questions or 500 questions, just a large question. And the person just doing that is just gambling. By the time you gamble for long, you get 50%. This mark is going to be 50-50. So that was the logic behind whenever you have 2 or 4 questions, anyone you miss, you are not sure, they will remove mark from it because logically, if they don't do that, anybody will pass. Even without reading it, just gamble. So far, the question is very large. You have a large number of questions. So it's the same thing. When you do many tests, there's the probability of one being significant is higher than when you do only 1. That's just a simple way. So look at when you are talking of 4 now. Imagine we have 4 groups, A, B, C, D. How many ways can you pair them? It's 6 ways. Even if you count it, either you use this formula now or you count it with your hand. A and B, that's 1. A and C, that's 2. A and D, that's 3. B and C, that's 4. B and D, that is 5. Then D, C and D, that is 6. So when you are having can use it now. When you now do 6 tests, your family-wise, your level of significance you set as 0.05 is actually 0.265. Instead of 5%, it has changed to 26%. Your error rate is 26%. That is, you have committed typo error. The probability of committing typo error has increased to, instead of 5%, it has increased to 26.5%. Now, if there are 5 groups, it's 10 combinations. You can try A, B, C, D, E. It's going to be 10 combinations. You can have 10 pairs. So your error rate is increased to 40%. Imagine there are 6 groups. You know what it means? If there are 10 groups, you are doing you are comparing them. You have to put it there 45 ways, and your error rate is 100%. That is, for sure you find something significant, even when it is not there. And that is what we call family-wise error. Family means that a family of tests are doing 3 tests or 5 tests, or 6 tests rather, 10 tests at the same time, 20 tests at the same time on the same data set, on the same issue. So there's no way you will not get some that will be significant. So your family-wise error increases. And that is why intelligent people now say, no, what shall we do? So they now came with this. Instead of comparing the 2 means directly, they analyzed the variance. And that is where the name comes from, analysis of variance. And that was it. I wanted you to understand this concept, and that was why I started with that simple t-test. What the meaning of systematic variance or variance between and unsystematic variance, which is the inherent variability, which is variance within. So in a data set, when you see variability, there are variance between, when you are dealing with groups, there are 2 groups, 3 groups, or 4 groups, there are variance between the groups, variability, there are variance within. So you're going to see now, when you are dealing with 3 groups or more, in fact, we have 3 levels of variability variance, which we are going to discuss. And that's the subject of ANOVA. ANOVA also calls F-test. Tells us whether 3 or more means are the same. It produces F statistic, which is similar to the T statistic in that it compares the amount of systematic variance in the data to the amount of unsystematic variance. That is, the numerator, which is systematic, compared with the denominator, which is unsystematic. I don't know if the English unsystematic is actually corrected. We are talking of that is not systematic. Now, F is the ratio of model to error. Now, if you remember, when I was explaining with t-test, I said the numerator is the systematic, the difference between the group. The other one is standard error. So another way of looking at it is that the error, the error there, and which is there within, you are comparing, you want to be sure that the systematic variance is far before you can say there's a difference between 2 or 3 groups, the systematic variance to offset the error, which is the error variability variance. It is also called F-test to reflect the name of the person that developed the technique. Fisher. This is the person. Sir Ronald Fisher. He's probably the cleverest person ever. Ronald Fisher was a geneticist. So many times I've told you that the biologists develop statistics, followed by social sciences. Biologists and social scientists developed statistics over the years because they needed statistics more than natural scientists like physicists, chemists, all those other ones. Though biology is in natural science also better. You know, biology share with physics, chemistry, the nomenclature, natural science. The biological science is different because of variability in the measurement. You know, if you remember in our lecture on the logic of scientific reasoning, we talked about phenomenon being studied following 2 types of models: deterministic model and probabilistic model. The probability model was something called stochastic model. That is, there's much variability. And that is what biological phenomena like blood sugar, blood pressure, whatever, and social science, IQ, many behavioral things, all those things, they are not stable. Just for example, now, if they talk about the composition of water, if they do the research in Toronto, it will give you the same, even if you come to just to do it, you get the same value. Because if you follow the H2O, is hydrogen and oxygen that make up water, is there. If you don't get the same, that should have you didn't use the appropriate method to get it. It doesn't vary, it's fixed. So most of these phenomena in physics and chemistry follow deterministic model. While for the social science and biology, it follow probabilistic model. For example, now, discrimination against HIV people, is it the same in Toronto and Nigeria? Even in Nigeria, it's not in the same thing in North and the South. Even in the same state, not the same thing in different local government. So different community. So you see, you have a glance now. Even the blood sugar, blood pressure, it varies. You see that some biological thing that even you yourself, if they measure your blood pressure now, within 2 minutes you are just seeing the same place. You will not get the same reading. So biological phenomena follow probabilistic model, and these people they develop statistics. Fisher was something else. People like Pearson, Spearman, all of them were geneticists, they were biologists. And that is why you use biology to go into statistics, because you develop statistics. It's not the mathematician in the environment of mathematics that develops statistics, though statistics is a branch of mathematics. The theory of ANOVA now, it examines the variation across all the groups at once using the concept of variation between groups and variation within groups. If there are no differences between the groups, then the ratio of the variance between the group and within the group should be 1, since the variation will be the same. What I mean is that the numerator is the variation between group. The denominator is the variation within the group, which is the one we talked about under error the other time. Now, if both of them are the same, of course, when you divide them, it will give you 1. The ratio will be 1. Variation between group divided by variation within group will be 1 if they are the same. If the group means are different, that is, if actually there's difference in the group means, because if the group means are the same, what will happen to that variation will be that it will be 1. When you divide the variation between by the within, it will be 1. But if the group means are different, with different you are looking for, you will not get, it will not be 1. Variation between group divided by the variation within group will be greater than 1, or it can be less than 1. Does it no, why it will be greater than 1 rather? It will be greater than 1. Because what is measuring is that it cannot be less. Because if it's less than 1, it shows that they are not different. There's no difference. So it will be greater than 1. Now, let me move. Why is this thing freezing? Sorry, the slide is not moving. It's freezing. Yeah, okay. Yeah. So ANOVA is an omnibus test. Omnibus test means that ANOVA is trying to test everything. You know, it's trying to look at the 3 group, or the 4 group, or 5 group. You want to know, it tests them at once. Is there any difference? Is there any difference among these 4 at once? That's why it's omnibus. Omni means all. It tests all at the same time. For an overall effect, or if there is or are any difference or differences among all the groups. However, it does not provide information about where the difference lies. When you do ANOVA, you may, for 3 groups now, you say, oh, there's a difference. They will not tell you, is the difference actually between A and B, or between A and C, or between B and C, or between all of them. ANOVA will not tell you that. You need to move further to be able to get that. I will talk about that. Then we'll talk about plan contrast or post hoc test. But ANOVA is an omnibus, so you just look at is there any difference among this group. So assuming 3 means are being compared, F ratio may tell us that the means are not equal. So it may tell you that, oh, they are not equal. That is, by 1, which is x1, which is mean 1, is equal to mean 2. It's not true. That's what it's trying to tell, because the non-hypothesis say that mean 1 is equal to mean 2, equal to mean 3. That's what you are testing, because you are testing now. But if it is not true, the F ratio will tell you. Now, however, there are several ways in which mean can differ. You know, it just tell you that it's not true, but we don't know. Is it between 1 and 2 or 3? Look at it. All the 3 means are similarly different. If all the 3 means are different, yes. The means of 1 and 2 are the same, but the group 3 has significantly different mean. The mean of 2 and 3 are the same, but group 1 has significantly different mean. Or the mean of 1 and 3 are the same, but group 2 has it. So the difference can be in different directions. So what ANOVA does is that there's a difference. It will not tell you where the difference lies. You need to move further to tell you where the difference lies. Now, I want us to look at an example. This is an example, libido score of 3 groups of participants with different interventions. So that we have 3 groups here. Maybe these 3 groups of people, 5, 5, 5. Group 1, 5 people, group 2, 5 people, group 3, 5 people. And these groups, they wanted to know the libido, the performance, you know what I mean, the how adult. Now, there's something, the Viagra, that can stimulate libido. So group 1 were given placebo, there's no active ingredient here. Group 2 was given low dose Viagra. Group 3, high dose Viagra. So leave that one. That's what they define the group. But the real thing that the score you are seeing is their libido score. Maybe they just ask them to rate their performance scale of 1 to 10. They give us the score. You look at group 1 now, you have 3, 2, 1, 1, 4. And the average, you had all the 5 together, value together, divide by 5, give you 2.2. And standard deviation of 1.3. And this variance is 1.7. That is when you just square the standard deviation. Now, group 2, you have 5, 2, 4, 2, 3. When you add the 5 score together, divide by 5, it gives you 3.2. The average is 3.2, mean 3.2, and the standard deviation 1.3, and variance 1.7. Group 3, the score was 7, 4, 5, 3, 6. And when you add all the 5 together and divide by 5, it gives you 5. So the standard deviation is 1.58 and the variance 2.5. Now there's something here. You see, there's, you know, if you look at the 3 group now, we are able to add each of them together and calculate the mean. It is possible for you also to add all the 15 together and divide by 15, it gives you the grand mean. Can you see that? So you have group mean. So when you have, maybe you have 3 groups or 4 groups that you are studying, you have the mean for each group. All those you can, if you collapse all the 3 groups together and you can have the grand mean, divide by the total number, overall total. It gives you the grand mean. So we have group mean, we have grand mean. We have the grand standard deviation and the grand variance. Now, this grand mean can also be calculated through another means. You can have the 3 means together and divide by 3, it will still give you the same. So there are 2 approaches to calculating the grand mean. Now, we'll explain this one and stop. The variability I want you to conceptualize now. From this data set, this slide you are seeing now, I ran it, you use Excel to prepare it from that data set. Because what prompted me to do this was, I was giving this workshop in Port Harcourt. I was explaining, I explained myself tired, people could not conceptualize. So when I went back to my hotel room, I have to now think, how will I do? What will I do? And I thought of, by the following day when I said, Kim, people just got it. And from then I prepared that. Yes, there. Look at it, just conceptualize this. You see the first column here is serial number. It's just serial number 1 to 15. This 1 to 15, you know there are 15 of them, 5, 5, 5. So the first 5, 1 to 5 is the group 1, the group 1 people. That's why I put 1, 1, 1, 1 in the second column. The next 5, group 2, this, and the last 5, group 3. So the X, you see the third column is the value of the libido we saw the other time. We just line them instead of putting in different groups, we just line them up. So these are the value. Now, we said that, we said we have each of the group mean, they have group mean. Then we have grand mean. So when we talk about variability, how do you measure variability? When you measure, the measures of variability are variance and standard deviation. And how do you calculate variance? You calculate variance by, when you calculate the mean, you now, each of these values, you remove mean from it, the deviation from it. The deviation from it, which is x minus x bar. Look at this, the fourth column. X minus x bar is the mean. The deviation is now x minus x is the original value of each first subject. When you remove mean from each, is x minus x bar. That is the deviation. Most of the, if you add all the deviation together, it will give you 0. Because mean is in the middle, as much that are higher than the mean are lower than the mean. So that's why intelligent people, okay, since we can, if you hide, give us 0, we square. When you square the deviation from the mean, it gives you square deviation from the mean. That square deviation, when you square, negative value vanishes. So the square deviation is what you add together and divide by n minus 1, which is degree of freedom, to calculate your variance. And the square root of variance is standard deviation. Now, what we, in this data set, that we are having 3 means and 1 grand mean, 3 group mean and 1 grand mean, I want to tell you that we have 3 levels of variance here. The 3 levels of variance is what we are looking at here. The first one is the variation within each group. So the variation within each of the 3 groups has its own variability within each group, which I was calling inherent variability. No, I was talking about standard error the other time. How do you calculate standard deviation versus square root of sample size? So in the inherent variability is the variability within. So each of the group has their own variability within. That is variability within, or variation within the group. Now, that is what we first of all demonstrate in this one. When, as we learned in this third column, the values, you calculate, if you look at it, what we did here is to remove the mean of group 1, which is 2.2, from all the 1 to 5, that group, those 1, the first group, they give us this. This one is to remove the 3.2, the mean for the other, the next 5. From this value, it gives you all this one. And the last one to remove the 3, the group mean for 3 from the value to give all this. If you now square them now, it gives you the sum of square, you had everything together. So what this one is measuring now is variance within each group. So within all the 3 groups, we look at the variance within. That's what. So the sum of square, before you go and calculate, this is sum of square when you square the deviation. Before you now divide by 1 minus n minus 1, which is the degree of freedom, to get your variance, at least it's called sum of square. So 23.6 is sum of square within all the groups. These are the groups. Now, that's first level of variance. The second level of variance is variance between. The between the different groups. And how do you know that? You remember that we have the grand mean, and we also have the group mean. So when you remove the group mean of each group from the grand mean, it is the one that is looking at the variance between. So what's happening here is for us to go and put that, for remember now, if you remember, for group 1, what do we have there? We have, if you look at group 1, the mean is 2.2. The grand mean is 3.4547. When you remove the 2.2 from the, it gives you this for the first 5. So the group mean for group 2, the number 6 to 10 is 3.2. When you remove it from the grand mean, it gives you all this. It gives you the same value because it's the same value for each of the for the group now. So the last one, the group mean for group 3 is 5. You remove it from the grand mean, it gives you this. Can you see now? It gives you this. Now, when you now square, it gives you this. This is variance between. So we have 2 levels of variance now. Here, we have just explained variance between, within rather, variance between. Then there is total variance. Total variance means, how do you know? You know we have grand mean. If you go and remove the grand mean from individual value on their own, you know, remember you can calculate the grand mean by adding all the 15 together and divide by 15. So if you remove that grand mean from all of them, from 1 to number 15, all of them, the two at the same time, it gives you the total variance. And the sum of square you are looking at, if you see sum of square within, which is this one, sum of square between, which is if you add it together, 23.6 plus 20.135, it gives you 43.7. The sum of square between and sum of square within add up to the total sum of square. I want to stop here because before you know it, now people begin to come into technical. So we'll talk further later how you now calculate the mean, the mean square from which is the variance, and how we calculate the F ratio. We discuss in the next lecture. But why I just discussed, I just want you to have the concept that, and that is why they call it analysis of variance, because you're analyzing the variances, the variance within, the variance between, and the total variance. That's why I call it analysis of variance. In the next lecture, we throw more light how these variances come together to calculate the F ratio. I don't know if there's any question. We stop at this junction. I don't know if anybody has chat. I didn't see any chat. So it means that it's very simple. So any question? I didn't see any chat. If you have a question, you can ask your question.
Hello, sir.
Go on.
Dr. Gani, sir, can you just go over which mean did you use to get that in between? I mean, I didn't follow it. I missed that part. The variance, when you are talking about calculation of the one that in between. I just want, how do you arrive at?
Okay.
Yeah, please, can you just go over it? So
what I say, if you remember the original data, we have the group 1, the mean is 2.2, as you can see. 2.2. For group 2, the mean is 3.2. For group 3, the mean is 5.0. The grand mean, for all of them is 3.467. Now, what I was not saying is that the variance within each group is the difference in the mean of the group from individual value. Individual value are what I have listed. If you look at it, what we have on this table: 32114, 52423, 74537 is 36. Is what I just lined up there. It's only that the first 5 is for group 2-1, the next 5 is for group 2, and the last 5 for group 3. So for each of them now, that's what I like. Can you see now? So for each of them, for the first 5, I remove their group mean, which is 2.2, group 1, from each value here to get X minus X bar. For the next one, number 6 to 10, which is the group 2, I remove 3.2, which is their group mean, from each value here to get what we have. And the last group, which is group 3, number 11 to 15, I remove their mean, which is 5, from each value to get what we have here. That is deviation from the mean. Some will be positive, some will be negative, because the value that are above the mean, when you remove mean from it, give you positive. The value that are below the mean, when you remove the mean, give you negative. The value that is equal to the mean, give you 0. When you add everything together, it gives you 0. But the intelligent people, they square it because you know that one has no meaning. So when they square the mean deviation, it remove the negativity. So everything will be positive, you're able to add it together. And that's what we call sum of square. So if you have been running ANOVA and regression, you will see come across sum of square. That's the origin, sum of square. Now, ANOVA, you get to know later that ANOVA and regression is the same thing. There are two faces of the same coin, the same thing. It's only that in those days, the experimental researchers use ANOVA a lot, while the observational researchers, non-experimental researchers, they use regression. They didn't know that they were doing the same thing. So later we got to know that, oh, it's actually the same thing. So it's a matter of time. The ANOVA will give way to regression. You will not use ANOVA. You will rather use regression because it's easier to use. There's worthy of understanding because in our lecture, when we talk about ANOVA, to understand, we also talk about regression. We move from ANOVA, we move to regression because it's the same thing. And that's why when you run regression, there is part of the hardware that you write ANOVA, analysis of variance. So now, here, what we have just done in this column 1 to number 3 and 4 is to try to look at the variance within. So what we have here, the total sum of square is sum of square within. That is the deviation of each group mean from each value, or deviation of each value from the group mean. Is the difference between the mean of each group from their value in that group. That is variation within. While the other one, variation between. You know, you are looking at and that is the one that is your systematic variation. That is the difference between these 3 groups. How do you know? For you to know the difference between 3 groups is for you to look at how do they deviate from the grand mean. It's just like the grand mean is more like a gold standard. So when you have 3, how do these 3, it's just like you have the standard, the gold standard. Now, you want to see the difference between these 3 groups. How do they differ? All you need to do is to compare all of them with gold standard. The one that deviates most from the gold standard, you know that if there is the deviation from gold standard very much, that should that you know that they are not the same. If the deviation from the gold standard is the same, that should they are the same. That's the logic here. So if you want to now look at the difference between the 3 groups, what you should do is how differ do each of these mean, the 3 mean, each of them, how do they differ from the grand mean? Yes, I mean now. So what you should do is to remove grand mean from each of the group mean. When you remove the grand mean from each of the group, like now when you review grand mean 3.47 from number 1 to 5 now, which is group 1. That's why you're having the same value from 1 to 5, 1.27 minus 1.27. You remove, you say 2.2 minus 3.47, which is the graph. It will give you negative value, minus 1.27. Now, when you do that for the group 2, which is number 6 to 10, you remove the grand mean from their group mean. Their group mean is 3.2. 3.2 minus 3.47, it gives you minus 0.27. You see that it's the same for all of them. Then the last one, the group mean of the last one is 5. When you say 5 minus 3.47, that one will give you positive value, give you 1.53. If you see add them together, it gives you 0. When you now square it here, it gives you the sum of square between, because it's what I'm looking at, variation between the groups. While the first one is the variation within the group. Now, the variation between the group and within the group, they should equal to the total variation. The total variation is the variation that is to be explained in the data set. And you can only know that all you need to do is to remove the grand mean from individual value. When you remove the grand mean from it, it gives you the total variation that is supposed to be explained. So the total variation is supposed to be will be addition of the variance within and variance within. And that's why you see sum of square within is 23.6, sum of square within is 20.1335, And when you add the two together, it's equal to the total sum of square. I think that's where we start. I don't know if I have answered your question. At least I thought.
Yes,
More
very
like
clear now. Very clear, sir.
That's great. So any other one? Any other question? Okay. If there's no other question, that shows that it's very simple. That's great. So we can stop here. Let me stop the recording.